The following question asks you to list the loop current equations for such a circuit. Let's have a review. The loop current equation is a KVL using virtual loop currents as variables. So we have self-resistance and the mutual resistance. With SSS, the self-resistance and the mutual resistance are expanded to self-impedance and the mutual impedance. Now we take loop 1 as an example. For I1, its self-impedance is this. I1 and I2 has a common branch. The direction of I1 and I2 on the branch is opposite, so there should be a negative mutual impedance. I1 and I3 have common R2 branch. I1 and I3 are opposite on R2, so their mutual impedance is also negative. I1 and I4 don't have common branch. The left part of the equation is the voltage drop along resistors, and the right should be the voltage rise on the voltage sources, so it should be US. The self-impedance in loop 2 is like this. Similarly, it's a negative mutual impedance. R3 is a common branch between loop 2 and 3. They are with opposite directions, so their mutual impedance is negative. There's no voltage source on loop 2, so the right term is 0. For loop 3, its self-impedance is like this. Similarly, negative R2 is a mutual impedance between 1 and 3. Negative R3 is between 2 and 3. 1 over j omega c is between 3 and 4. I3 and I4 are opposite on this impedance, so we have this. There isn't a voltage source in loop 3 too, so the right term is also 0. I4 loop is easy because I4 is the only one loop passing the current source. But the direction of I4 and IS is opposite, so we have this. We have finished the loop current equations of the circuit. Let's compare the discussion in lecture 34. We can find that all the basic concepts are the same, except we change the self-resistance and the mutual resistance into impedance respectively. Likely, we can expand the known method in lecture 33 into the SSS. We only need to change the self-conductance and the mutual conductance into the self-admittance and the mutual admittance. Next, let's analyze a standard SSS circuit. This is a parallel of a resistor and a capacitor. A resistor and an inductor are in serial connected, and then two parts are serial connected. The voltage RMS is 100 degrees. The angular frequency is 314 rads per second. We are asked to find the time domain expression of all branch currents. In order to solve this circuit, we need to transfer the original circuit into an SS model. It's like this. For the inductor, its reactance is this. For the inductor, its reactance is this. So we can find the ZEQ, seeing from the source to the right. We've discussed this in lecture 63. The result is this. So we know we can mark the reference direction of I2 and 3 in the figure. For the SSS solution of I2 and 3, we need the current division equation for two impedance. That is this. And similarly, so we can write the time domain expression of steady state I1, I2, and I3. That is this. Before finishing the problem, we need to provide an explanation for the zero initial angle of the voltage. The problem doesn't provide any initial angle for the circuit, so we need to appoint an initial angle. What we need to emphasize is that if the initial angle of the voltage source is not zero, all the time domain expression of the currents will be changed accordingly. But with the analysis, you can see that even though the initial phase angle is variable, the phase difference is unchanged. The RMS value is unchanged. In this sense, it doesn't matter what is a voltage initial angle phase. From the perspective of simplicity, we can just set it as zero.